Hello everyone. In this video, we will learn how to analyze a continuous time system using the Laplace transform. And we will learn the following topics. First, what's the definition of the Laplace transform? The mathematical definition and the physical meaning of it. And basically, it's if you have a signal in the time domain, then there is a mathematical technique that will convert it to the frequency domain or the Laplace domain, x of s. Here it tells you about the signal change over time. Here it will tell you the frequency content of the signal. Then we will learn about the property of the Laplace transform, and some of the property will help us do system analysis. Then we will learn the power of Laplace transform by solving differential equation. We saw in the time domain, it's time consuming and many steps just to do a second order system. In Laplace domain, we can solve a fifth, sixth, seventh order system easily. Then we will do analysis of electrical network. Now here, block diagrams and system realization. If a design engineer give you H of S, these describe a system. How can we build this physical system? And that's what system realization. Take it from this mathematical model to a real life system. Then we will move to the frequency response, which is a special case of the Laplace. Laplace, if S equals sigma plus j omega, where sigma is the decay rate, omega is the oscillation rate. If we set sigma to 0, now this become just the frequency response. So H of S become now H of j omega. And that's Laplace domain. This is the frequency domain, the Fourier transform domain. Then the last topic would be filter design by placement of poles and zeros. So now your client came to you and said to you, I have this type of inputs, I need this type of output. Can you design a system that will take this input and give me this type of output? We will learn how to build this system by using this technique, poles and zeros placement. In this video, we will cover the Laplace transform, and in future videos, we will be covering the remaining topics. Okay, let's just get some idea about the Laplace, what it means. You have the signal in the time domain, you do the Laplace transform, now the signal become the Laplace domain, x of s, where s here is just sigma plus j omega. We call this the complex frequency. This is the rate of decay, and omega is the rate of oscillation. So you can think of the Laplace domain as an indication of the different frequency content on the signal, x of t. So if I have all these exponential, which is basically ESI, SI could be, for example, let's say S1 is 3 plus J4 and or minus 3. And if you plot it, it may look something like this. Now this has different frequency content, and each one of these has a strength, which is this one, x of SI. So x of S1 is just the strength of this signal. I may have another signal that looks maybe like this. So now here S2, it will have different frequency. It could be minus 4 plus J10. Then x of S of 2 will have a different value, which is the strength of this one. Now, if I have the signal in the time domain, I can represent it as a linear sum of these exponential signals. Each one of them has a different strength, x of SI. That will be the Laplace domain of this signal in the time domain. So it just basically show you the strength of the different frequency component. Here the frequency is complex. It's not just oscillation. It has oscillation and decay. If we look at these different signals here, for example, this is just a DC 1. So you can think of it as sigma is 0, omega is 0. These just give you 1, which is a DC. Now this signal here, it has a decay rate sigma minus 1, but no oscillation. Omega is 0, so you just get this line decay. If you look at this signal, you can think of it as sigma is 0, no decay, but the omega is 5, oscillation, and the strength is 1.2, which is this one, the strength of it. And these signals here, you can think of it as sigma is -1 and omega is 5, and the strength of it is 1.5, and so forth. Now, if I add all these signals, I will get this signal, x of t. So now you can see x of t is a linear sum of these different exponential, and each one of them has a different strength. This is strength 1, this is 0.8, this is 1.2, 1.5, 1.5, 0.7, and so forth. So that's the link between the Laplace domain and the time domain. In real life, if you have a sensor and you are measuring maybe radiation from galaxy or temperature or wave from underground, you will have this signal in the time domain. That's what the sensor will pick. But now I want to know if this signal here is present here or not. And if it's present, it will tell me something about the mechanism that generates this signal. And that's why we need the Laplace domain. We take the signal in the time domain, we find x of s. That means I will know how much of each one of these is present in this time domain signal. That's what x of s will tell me. And then that will tell me the mechanism in the system that generates each one of these. Okay, now for system analysis, why do we need Laplace transform? We need the Laplace transform because it will tell us the frequency content of a signal x of t, and by looking at the frequency content, it will tell me a lot about the system that generates this x of t. Or I can use it in system analysis later on. So in the time domain, we said any signal x of t can be represented as a linear sum of these impulses at different locations, and the strength of these impulses is the sample of the signal at that instant of time, n capital T. So that is the signal in the time domain. I can represent it as a linear sum of these impulses. And that's what this equation is. Now in the Laplace domain, any signal in the time domain can be represented as a linear sum of exponential. One sample of this exponential could look like this. If I add different signals of this shape, but different oscillation, different decay rate, that means different sigma, different omega, and each one of them has a different strength, if I add them up, I will get x of t. And then we say this is the Laplace domain. We have this. Now for system analysis, we can do the following. If I have the impulse response h of t in the time domain, to find the output of this system, it's just the convolution of the input with the system impulse response h of t. And we saw convolution is a little bit complex, not easy to carry out. Now if we do the same operation in the Laplace domain, it's a little bit easier. Why? Because we don't carry out convolution. Now it's a multiplication. So first we take the signal in the time domain, we do the Laplace transform, we find it in the frequency domain. Same thing, we take the impulse response h of t, we do the Fourier transform, we get h of s. Now this we call the transfer function. Then what is the output in the Laplace domain? It's just a multiplication of x of s with h of s. Okay, so we got y of s. But if I try to listen to y of s, if that was a speech, I will not make any sense of it. I probably won't even hear y of s. So then we do the inverse Laplace transform to get y of t. And that will be y of t. So x of t could be a speech with noise. H of s will get rid of the noise. And then I get a clean speech, y of t. So that is the main advantage of the Laplace domain. It's the simplicity of finding the output from the input and the transfer function of the system. So let's look now at the definition of the Laplace transform. Now, two-sided Laplace transform of x of t mean x of t exists for negative t and positive t, something maybe like this. Now this definition tells us what? It says you take x of t, the original signal, you multiply it by a different exponential, could be something like this, then you integrate and you will get a value. That value will tell you how much of this signal is present here, and that will be x of s. And s here could be just any frequency. S is sigma plus j omega. So maybe I was curious about -1 plus j3, which is this one. So if I multiply x of t by this exponential, I get a value that will be the strength of this signal here. Now I may want to find, how about this? Now here s will be different. It probably minus 0.5 plus j 0.1, low oscillation. In this case, again, this integral means I take this signal x of t, I multiply it now by this one and integrate, and I will get a value. That value will tell me how much of this is present here. And that's what's the Laplace transform. Now, if the signal x of t exists only for positive t, like this, then here the low integral will be 0. And now we call it unilateral Laplace transform. Okay, now let's say we have x of s. Can we go back to the original signal x of t? Yes, we do the inverse Laplace transform. And that is the definition of the inverse Laplace transform. Basically, you take x of s and you multiply it by es of t, another exponential. Here it's e minus, here it's e, and you integrate. But the integral here is a line integral, and we don't teach it usually in undergraduate courses. So in this course, how do we find the inverse Laplace transform? We do the partial fraction expansion, which we will learn it, and the table. Let's take some examples to demonstrate how to find x of s. So find the Laplace transform of this impulse. So we have an impulse here. That's x of t. And we need to find what is x of s. In this case, if I carry out the definition, x of s equal the integral minus infinity to infinity x of t e minus s of t dt. So that's the definition. So this will be minus infinity to infinity. Now, this impulse exists only at t equals 0. And the impulse time any function, you get the impulse back again, time the value of the function at t equals 0. So if I plug for t0, this will be just 1. Now the integral of an impulse, you just get the area under the impulse, which is always 1. So that's x of s. So for an impulse in the time domain, the Laplace transform is 1. What does that mean? That means for all value of sigma and omega, x will be always 1. So if I plot sigma here, j omega here, and this is x of s, then it will be just always 1, no matter what is sigma, no matter what is j omega. Let's plot this here and this is here. So that is 1, let's say. So it's going to be a surface plane like this. It will be 1 from this plane, 1 up, and it's just going to plane goes to infinity. That means that simple signal in the time domain has all frequency content of different sigma that goes from minus infinity to infinity and different omega oscillation rate. Now, what about if we want to find the Laplace transform of the unit step function u of t? X of t is 0, u of t is here. Since the signal exists only for positive t, so that will be from 0 to infinity. X of t in this case is just u of t, e minus s of t dt. So that's the definition. So u of t in this range from 0 to infinity is 1. So this is just 0 to infinity e minus s of t dt. And the integral of this one is just 1 over minus s e minus s of t evaluated from 0 to infinity. This is equal 1 over minus s plug for t infinity minus plug for t 0. Now this term we have no problem with because it's just 1. So that's minus 1 over s. How about this term? Well, this will go to 0 only if s is larger than 0. Because when s is larger than 0, then this will be just e to the power of negative infinity, and that will be 0. So that will be 0 only if this is true. So what does mean s larger than 0? That means sigma plus j omega larger than 0. J omega just oscillate, so it will never go to infinity. But sigma may cause it to go to infinity if it's positive. So that means the real of s, which is the same as sigma, must be larger than 0. In this case, x of s will be minus 1 over s minus 1. That's just 1 over s, which is this. And make sure when you solve it, you indicate the region of convergence is real of s is larger than 0. So if I want to plot this, the frequency content of a unit step function, so let's plot. Here is sigma, here is j omega. Now if I plot the magnitude, first let's express s as sigma plus j omega. Then the magnitude will be 1 over the square root, the real square, that's sigma square, plus the imaginary square, that's omega square. Now, sigma must be larger than 0. And as sigma increase and omega increase, the whole thing here will go to 0. So as sigma increase, omega increase, the magnitude will go to 0. But if they are close to 0, if sigma is like 0.001 and omega is 0.001, then this would be very large. So we expect the plot of these to be something like this. A surface plane like this. It has a peak when s close to the 0, but it has to be larger. Then as sigma increase and omega increase, it starts just decay to 0. What about this region here? It doesn't exist because this condition must be met. Sigma larger than 0. So that is only in this plane here. This plane, there is no values for x of s. Okay, let's continue. Take another example. Find the Laplace transform of this signal. Now again, let's write the definition. X of s equal minus infinity to infinity. The signal x of t is just e a of t u of t time e minus s t dt. Now u of t exists only for positive, so this is unilateral. Here I'm assuming a is a negative value. Okay, so that's 0 to infinity a minus s t dt. U of t is just 1 in this region. And the integral will be 1 over a minus s ea minus st from 0 to infinity. So this is 1 over a minus s plug for t infinity minus plug for t 0. So again, this is e to the power of 0 is just 1. So this is just 1. How about this? E to the power of infinity. For these to go to 0, a minus s has to be less than 0. So a minus s has to be less than 0 for that exponential to be 0. So then the condition is a minus s less than 0 or s larger than a. That's same as s larger than a. In this case, x of s will be this negative here when you multiply it by this, I can write it as 1 over s minus a, as long as s larger than a, or the real of s, which is sigma, is larger than a. Then that will be the Laplace domain of this signal. And the region of convergence, this is the region of convergence here. Sigma is larger than a. And if I try to plot this one, let's see, it's gonna look something like this. Here a is minus 5. So the Laplace domain is 3 over s minus a, so minus time minus 5 is plus 5. If I want to find the magnitude of this one, I express these first as 3 over s is sigma plus j omega plus 5, and the magnitude will be 3 over square root the real part, which is sigma and 5 square, plus the imaginary square. So that is the magnitude. If I use MATLAB and plot this for different value of sigma and different value of omega, as long as the region of convergence, that means sigma is larger than a. In this example, a is minus 5, so sigma is larger than minus 5. So this is minus 5 is here. So there is nothing here. I don't plot anything because that's not the region of convergence. So that's just 0 here. And now sigma has to be larger than minus 5, but let's say minus 4.5 plus 5, that will be the lowest value for the denominator. So the whole thing will be peak, and that's the peak here. When sigma gets closer to the minus 5, that's where you find the peak. Now, as omega increase and sigma increase, then the denominator will increase and the whole thing here will go to 0. And that's what is this. This is sigma, this is omega. So as omega increase, it drop down. As sigma increase, it just keep going down and down. And the peak will be around sigma equal 5. In this plot, I showed minus 4. I didn't plot like minus 4.5 or minus 4.9. All right, we demonstrate here how do we find the Laplace representation of a time signal. Let's take one more example, which is find the Laplace for this cosine omega 0t u of t. So let's clean up. Okay, let's find the Laplace transform of this signal. So if I plot this signal, it looks like this. And this is 1. And the oscillation rate is omega 0. Okay, I can express this signal as follow. So I just use the trigonometric property. Now I can call this like A1 and call this like A2. So this will be just half EA1t plus EA2t. And to find the Laplace transform of this one, I will use this property. See, I already find the Laplace transform of this signal and I found it to be this one. Now if I call this x of t, now this would be x of s. Half 1 over s minus a1 plus 1 over s minus a2. I'm using this fact. Now let's plug. This will be 1 over s. We said a1 is just j omega, so that will be minus j omega plus 1 over s minus a2 is minus j omega 0. Now if I add these two terms, I can unify the denominator just by s minus j omega 0 times s plus j omega 0. And here it will be s plus j omega 0 plus s minus j omega 0. And finally this will be, this is just a complex times its conjugate, so you get the real squared plus the imaginary squared. and this plus will cancel these and you get 2s, and this 2 will cancel, and finally you get s over s squared plus omega 0 squared. Now if you plot these in this s plane, it will have many components, but it will peak at omega 0. Now, even though in the time domain, it sounds like only one frequency component, where all these frequencies are coming? They are coming because these doesn't oscillate to infinity. No, it starts at u of t. Because of that u of t here, it is 0, 0, 0, then sudden jump, then a cosine. That 0, 0, then sudden jump cause this extra frequency when you plot this one. It's not that you will get, for example, omega 0, if that is omega 0 and sigma is 0, it's not you're gonna just get an impulse like here, one frequency component. You will get a plane, but it will peak somewhere here, then it goes to 0. Okay, now in this table there are many popular signal x of t in the time domain, and this is the Laplace transform. So now how do we find the inverse Laplace transform? So let's assume you have a signal x of s and that is given. And now I want to go back to the time domain. How do I find the inverse Laplace transform? We will do it by partial fraction expansion. That means if you have a signal x of s, then try to simplify it as a linear sum of any of these signals. And we will be using partial fraction expansion technique. So if you simplify it as a linear sum of any of these popular signals, then you can use the table and find the inverse Laplace transform of each one of them. So you have x of s, you break it down to simple signal that exists here, and then use the table to find x1 of t plus x2 of t plus x3 of t. And if you add them up, you will get the signal x of t. And that's what partial fraction expansion. Thank you for watching, and in the next video we will be talking about the inverse Laplace transform.